for example, high-speed railway and some deformation-sensitive highways as well. In transitions between pile and non-pile structures, because the pile structure will settle very little, and the non-pile embankment could induce a lot of settlement. So there could be a big differential settlement between these two parts, which have to be addressed. And typically, there will be a transition of piling to the ground support. Another example is widening or connecting into existing embankments. Existing embankments would have undergone complete consolidation settlement, while the new embankment would be experiencing gradual consolidation settlement. And to match that and remove that differential settlement, a pile embankment is commonly used. And in some cases where you have a back-to-back retaining wall, where there is no space to widen the embankment sides, then a pile foundation is also commonly used. Pile embankment sounds like a very solid support, but they need to be designed correctly and adequately to avoid problems as seen here. You can have the soil, subgrade soil underneath the pile embankment being eroded away and buckling of piles and so forth. Again, as in the part 1, I will be using the BSA 006 Code of Practice to illustrate the design concepts. In BSA 006, there are 6 check criteria, out of which vertical load shading will be the important one and will be discussed with other design approaches and codes as well. Starting with check A, the piles have to carry the load of the embankment. So there should be sufficient pile load capacity, and you can approach this first by defining the pile spacing, or you can choose the pile that you want to use with a known capacity and work out what is the pile spacing required. Next, the check B involves edge stability. It concerns the question of how wide or the extent of the pile section to the sides of the embankment. Obviously, you do not need to go all the way to the toe. But what is important is if there's any edge stability that happens beyond the edge pile cap, then it should not affect the embankment top, whether highway pavement or the rail track is constructed. And the code has got equations to allow you to do this check. This is a photo of a very brave gentleman. He is sitting actually under a embankment. We searched here. The steel columns are representative of the steel pile support, and you can see the undulating surface above his head. That's the reinforcement geotextile, and this is a fully monitored, instrumented trial where strains are measured and to learn more about how pile embankment works. Arching models. Soil arching happens when you have got differential vertical stiffness in the ground. And there are few arching models that I'd like to talk about. The first one is on the top left, where there's no soil arching. So only the column of soil directly above the pile cap is transferred onto the pile cap and then the piles. And in between that, it is the subgrade that is taking the load of the soil. So the area that is not supported by the pile cap, it will settle, and you will get what you call mushroom stools seen above the embankment top. Then you have the trapezoidal arching, and what forms is a shallow trapezoidal area where most of the embankment load gets transferred onto the pile caps, and only a small portion of the soil gets onto the subgrade. Then you have got the single shell arching, where a dome forms, and here you can see a larger area of the soil being where the weight is transferred onto the subgrade. And lastly, there is recently the multiple shells arching, or concentric shell arching, where multiple shells form and they get transferred onto the pile caps, and only a small portion of the soil weight is loaded onto the subgrade. Check F actually involves avoiding the situation where no soil arching happens, because if that happens, you will see this road, the mushroom stools are forming, and they continue to become bigger even after the pavement has been put on. And these days, when embankment fill are used, they are properly selected and compacted. So this no arching ability is unlikely to be due to the field. What is possible is that the embankment is too thin in relation to the pile cap edge spacing, and BSA 006 provides a recommendation to avoid this. And it is a ratio of h divided by 0.7 times the pile spacing minus the pile cap distance that needs to be greater than 0.7. So we know that a certain portion of the embankment field load does not get transferred directly onto the pile cap top by arching. So that load has to be carried by the reinforcement that spans that gap. And BSA 006 also provides a calculation method for that. And for example, the BSA 006 arching is based on the Marston's arching model for buried rigid conduits. There are two arching equations that are given in the original BSA 006 code, and more recently, Lawson has provided a chart form to smoothen out that two equations. And BSA 006 is based on the combination of single shell arching and a uniform load distribution onto the reinforcement geotextile. And this chart gives the Lawson's chart, whereby the arching ratio is plotted to the factor of x divided by a, and you can read off the value to be put into this equation to find what is the design working load that is required in the reinforcement. It's quite simple, actually. Check C involves the horizontal thrust. The embankment has got a push sideways, which can do a number of things. It can actually push the piles away sideways and fill the piles. And this outward thrust has to be taken by the reinforcement as well, in addition to the value of TRP that we just talked about just now. The embankment, this is showing you the effect on the piles if you have not adequately provided to resist or restrain this outward push. The direction of laying is also very important, and it depends on whether you are using single pile caps or linked pile caps in the form of pile capping beams. The linked pile caps will link together a group piles, and if it is the single pile cap, you can see here in two different colors, yellow and red. You need reinforcement to be taken up in both directions. Whereas in the case of linked pile caps, especially when the pile caps are across the embankment, then the pile cap will take care of the lateral push, and you only need spanning across one direction. So likewise, in the case of single pile caps, you need to be laying the reinforcement out in two directions, orthogonally to each other. And the reason for this is the geotextiles reinforcement have a limited roll width, and even if it is equally strong in both directions, you need to be jointing the roll edges, and that weakens the strength transfer. And so typically you are providing the reinforcement strength in the main direction or the rollout direction. So you need to roll it out in the areas that in the directions that you need the tensile strength to resist whatever forces. This concerns check C, and it is about bond length or anchorage length beyond where the piles are used. Otherwise, it will slip in, so you have to provide adequate bond length or anchorage length. And again, BSA 006 have provided equation for you to calculate this. That was the bond length along the embankment. The bond length across the embankment is equally important, and sometimes the edges may not have enough soil-to-soil contact for adequate bonding, and in this case you will be wrapping around back into the embankment with the truss block sitting on top of the edge pile cap. This is check D. It concerns the tensile load, which I mentioned just now. It is the outward push that the TDS, and you have to also check that the field should not slide outwards over the reinforcement on top. This is a check that is rarely necessary, but for completeness, BSA 006 provides this check, and it checks the overall stability or global stability with a slip plane that cuts through the reinforcement and the piles as well. Right now, I'll talk about different arching models that are available for different approaches, as well as load distributions for the load shading. There is Collins' approach, which uses the trapezoidal arching, and then the unarched portion is uniformly distributed onto the reinforcement. Whereas the BSA 006 is more conservative. It has a bigger arch dome, and there's more load that gets transferred onto the reinforcement, also with a uniform load distribution. And the ABGEO approach involves the multiple shells arching, and the load that gets distributed onto the reinforcement is assumed to be triangular form. To compare these various different approaches, there are these two charts, and it can be shown that the Lawson's BSA 006 approach is quite conservative compared to, say, ABGEO and Collins. Some additional pointers. Generally, in design, the subgrade support is ignored for reasons of there's a possibility that the subgrade material is washed away. Embankment fill cohesion is ignored also. That's because if the embankment base or bottom is flooded and soaked up, then in a saturated condition, the cohesion is close to zero or zero. During the initial stages of embankment construction, embankment height is insufficient to develop much arching, and provision of reinforcement helps stabilize soft subgrades. It also allows compaction of backfill to standards and promotes early arching formation. So it is not just the final stage where reinforcement has a benefit. During the construction, it is also valuable in that you are able to compact to the proper standards. Generally, for reinforcement, the wider and the longer the rows, the better it is. You want to try and avoid as much overlaps or joints as possible. When GeoGrid is used as reinforcement, sometimes you may need to additionally use separation geotextile like ground level, because GeoGrid has got huge openings and they do not separate or have the separation function. The Collins approach is based on a stiff beam approach and may not be compatible with most practical conditions for pile embankment. What it does is it underestimates the load that is required in the reinforcement. And more interestingly, in recent years, there has been research that shows that, especially done by Van Ekkelen, the multiple shells arching model with inverse triangular load distribution gives the closest match to physical model testing. And having said that, BSA 006 design method has been the longest and proven method of design and deemed conservative. Here's the test lab where Van Ekkelen did a research, and it is a combination, as I mentioned, the multiple shells arching plus the inverse triangular load distribution. This is different from the ABGEO, which has the load shading more towards the center of the reinforcement, whereas the Van Ekkelen's model of the inverse triangular load shades more load onto the stiffer areas close to the pile caps. On the laying of geotextiles, it is important to lay in both directions if they are single pile caps, and typically you will not you do not want to have joints in the main roll direction, because once you join, you lose efficiency. In the cross direction, usually you can handle that because a roll length is typically much longer than the width of the embankment. But in the and you can easily use one single piece, and you also need the reinforcement laid in the longitudinal direction. On the edges, PSA 006 has given two examples of anchorage. One is using the truss block wrapped around, and another one, a more recent one, is to form a trench for the wraparound of the reinforcement back into the embankment. The question of what if the length of the road embankment is longer than the road length. BSA 006 hasn't really addressed this, but the CUR 226, which is the Dutch code, has. And while you would normally not want to have a join, but if it is unavoidable, then the recommendation is you want it to span two spans or over 3 pile caps. And the Dutch code also provided some recommendations for how to treat a curving embankment. And there are two examples. One is a large radius, and another one is a small radius. What you can see here are the pile caps and the roll being laid out. Now I will go on to show two case studies. One is in Bangkok. Some bridges were built over the Chao Phraya River at Wat Nakhon Inn site, and these are all on piles, including the bridge abutment. And the embankment that goes that is built to meet up with this bridge abutment, it has utilized the pile gradual transition pile method, where closer to the ground part, the piles are shorter and wider apart, and as it comes close to the bridge abutment, they are piled to set and also at sufficiently close spacing. So it builds a transition, gradually transferring more and more of the embankment load onto piles from the right side here to the left side here. Here are some photos showing the installation of piles. The pile heads are cut off and ready for the casting of the pile caps, and the laying of reinforcement once the pile caps are done and filled in between, and then this shows the completed highway section. And this pile embankment has been around for more than 10 years and performing very successfully. Another example is an example from the Netherlands, and this is an road embankment with piles driven to the firm stratum, and here you can see the pile caps and the laying of the geotextile reinforcement in two directions. And the top photo shows the pile cap, and the bottom shows the field being leveled off to the top of the pile cap for the laying of the reinforcement. Right, that completes the pile embankments section. Now I'll move on to subgrade stabilization. Subgrade is the formation level soil. It can be in situ or recompacted backfill, as in the case of embankment that is underneath the load transfer structural layers. And here, gravel is typically used as a load transfer layer. This is a cut section of a road pavement. You can see here, this is a subgrade, the base course, which is basically gravel, and a thin surfacing, which is asphalt. It provides all-weather traffic support. The gravel layer also distributes the load to reduce the intensity of the road as it meets the subgrade. And the whole system provides you riding comfort and safety. And this is a diagram that shows the load distribution down to the subgrade level. And it is the subgrade that ultimately supports the imposed traffic load. But as you can see, this is being distributed to a wider area, so the intensity is smaller. And there are various examples of such load support systems. For example, unpaved roads, construction platforms or other load supporting platforms, paved roads, railways, ports handling area, and airport aprons and taxiways, all with the same principles. I'd like to now talk about the load transfer structural layers. They are basically specification control that limits the fines content to a very low percentage, because it is the fine materials that get affected by moisture and can lose a lot of the strength if it is wetted up or saturated. And with the gravel layers, we have a choice. We always can select. But with the subgrade soil, we have to work with whatever is on site. And the subgrade soil with significant fines can give rise to the following issues. The CBR value is drastically reduced when it increases in moisture content. And when you have a lot of expensive clays in the subgrade, then the subgrade can heave or shrink depending on the moisture content that is in the subgrade soil. And these two can give you a lot of problems in designing, say, for pavements and railroads. I'd like to talk a little bit about soil capillary action. We all know that there is capillary action in the inner of tubes, tubular sections. This is because water tends to stick together as a drop, and capillary action occurs when the adhesion of water molecules to a uniform circular glass tube wall is stronger than the cohesive forces between water molecules. And the smaller the tube diameter, the larger is the surface tension, and the higher the rise. In soils, the same thing happens, and this is because the finer the soil grains, the smaller the paths, and the greater the soil capillary suction, and the higher is the rise in the capillary rise, as in clay, which has the smallest grain size. I'd like to show some of the subgrade stability problems that we have to deal with in subgrade stabilization. Here you have a case where the subgrade bearing capacity is not enough and there's failure punching in. Or if the under the dynamic load of the railway passing, mud can be pumped from the subgrade. You can also have pavement surface cracking from excessive subgrade deformations. And also, if you are in expensive soil, not a soil that you have to pay a lot of money, but it expands or swells up. This pavement can heave, and it can give you a lot of problem. And typically, it is the bentonite clays that are causing this type of problems. Subgrade stabilization is the improvement of the load supporting capability of a poor subgrade. And there are traditionally a few methods of subgrade stabilization, say for example, mixing with lime, fly ash, and cement. And also more recently, subgrade stabilization with geosynthetics. And the geosynthetic solution, which is in this side, are generally, with the exception of geocell, more economical than all the others. And this is from a report that is done in the US, and the reference is White 2012. Subgrade stabilization with geosynthetics. This is the use of geosynthetics to improve the load supporting capability of a poor subgrade. Here we need to talk about what the geosynthetics can provide in terms of benefits or functions that can help improve. And basically, geosynthetics can be a separator. It physically separates the good gravels from being affected by the soft clay or mud below. And under dynamic load conditions on a saturated ground, you can have a case of mud pumping, whereby even though in a static condition they stay separated, but the dynamic loading can pump up or suck up the mud and contaminate the gravels. And once you have got the gravel contaminated, it loses strength dramatically and it won't function as well. And that will translate to faster failure of the pavement. The geosynthetics can also be doing a mechanical strengthening of the subgrade through either reinforcement of the subgrade or a lateral restraint of the gravels at the subgrade interface level, as shown here. And lastly, moisture control. As we know, as we have been discussing, if the subgrade has got expensive clays, then if you allow moisture to seep into the subgrade and you don't control that, then you can have problems. And more recently, geosynthetics are designed to also have the wicking and drainage capability. Wicking in the sense that it will suck up moisture from the subgrade and also bring the moisture out to the environment or atmosphere. What are the geosynthetics that are used typically in subgrade stabilization? You have conventionally the geotextiles, the geogrids, and also the geocells. As we have seen, geocells tend to be expensive to use, so more likely you'll see either geotextiles or geogrids. And in geotextiles, you have the conventional nonwovens and the woven geotextiles. In these woven geotextiles, for subgrade stabilization, I like to emphasize that it is the high modulus woven geotextiles. Typically, the modulus at 2% elongation is used as the standard yardstick, and also woven geotextiles with a very rough textured surface for lateral restraint. And also, to combine further different functions, you can have composites. And composites are formed with geogrids as well as with geotextiles. Key points. For separation performance, you want the fabric to have very small pore size that can prevent the intermixing. And for separation, geotextiles are used. Geogrids do not separate. A non-woven geotextile is more effective for anti-fouling performance as it has got smaller pore size as well as a more tortuous path in the cross-plane direction. And I mentioned just now, for strengthening of subgrade, it is the high tensile modulus at 2% strain that is governing. And both geogrids and woven geotextiles are used for this purpose. For lateral restraint and gravel at interface with subgrade, additionally, high interaction efficiency is required, and the geogrids with the rough textured woven geotextiles are used. And for moisture control, it is the fabrics that have got a wicking function and in-plane conductivity, in-plane permeability that is used. Composites are formed to enhance basic products with more combined geosynthetic functions. The design approach, I would like to talk about that now. The self-weight of the load transfer structure layer constitutes permanent load on the subgrade. The traffic load constitutes temporary load or temporary stressing of the subgrade, because once the traffic load have moved on, then the load is relieved. The design approach, it depends whether it's stability related or serviceability related, or by serviceability I mean deformation, surface deformation related. In the stability related design, for example, you are designing for a construction platform case, then you need to check for localized bearing capacity, global slip failure if the construction equipment happens to go too close to the sites, and you are designing for permanent and temporary load combined, and you need to design with adequate factor of safety against ultimate failure. For super soft subgrade, which covers the undrained shear strength below 5 kPa or 5 kilonewton per meter square, special construction technique may be necessary. And in this stability related design, design can be geosynthetic product generic. Then you have got the serviceability related design, where surface rutting and track settlement governs. Traffic load governs. It is the cumulative plastic deformation from the traffic passes that are important, because when the load comes on, it presses or compresses the subgrade soil, and then when it goes off, there's a certain rebound, but there's a certain plastic portion that remains. So this plastic portion of the deformation keeps accumulating as more and more passes goes past that spot. And when you have got subgrade soil that swells, then you need to have a geosynthetic that has got moisture control capability. And for this, the design needs to be geosynthetic product specific and application specific, because the performance of each of this product and what functions they provide is the key. So it is the product needs to be specific. I will talk about this localized bearing capacity. Here you can see a diagram where the construction equipment loading is on top of the structural distribution layer, and the thickness will determine how well this is distributed, and as it is distributed, the intensity reduces, and given by this equation. Then the factor of safety for localized bearing capacity can be given in this equation, and it needs to be greater than 2. Stewart, Williamson, and Money provides the recommendations that the bearing capacity factors when geosynthetic is not used in soft subgrades is as low as around 3, and when adequate reinforcement is provided, it can go up to 6. So you can quite clearly see the benefit of the reinforcement portion of the geotextile, and what tensile strength it needs to be able to carry. In the same case as the pile embankment design, you want the reinforcement to be able to pick up the outward push of this load, as well as to try and bring in an inward shear stress from the underside. So this will allow you to work out the tensile strength required. When the construction equipment is too close to the edges, then you may have a case where a slip failure can occur, and this is very similar to the basal embankment reinforcement check that we talked about a few hours ago. And this is designed using computer software, RESA, or SW, typically to a minimum factor of safety of 1.3 to 1.5. Here, I want to show you the special construction technique for super soft soils. You'll first start with a reinforcement fabric that is all sewn up, and here the seam strength is very important. They are laid over the pond in this case, and then stabilizing berms at the sides are formed, and then filling is advanced in finger berms here, and once you have reached the other side, you can start filling in between the finger berms. And here the whole idea is you want to limit the mud heaving that actually will happen when you put fill on top of. And you can here very easily imagine that if you don't have the fabric, then it will be all messed up. Next, I'll talk about some examples of serviceability related design. Here, I'm going to talk about um, two cases, one for unpaved road and one for paved road. In the unpaved road, the Jiruhan design method is the most common design method, and while it is product specific, the design itself is generic. So what is important is that the product has to be specifically calibrated with the design to give a certain input value for the design. And our company has got in-house softwares that does that quite easily for you. And for pavements, for paved roads, the standard AASHTO design method can be incorporated, can be used with the incorporation of geosynthetics. And likewise, while the design method is generic, the product benefit is specific. So it needs to be calibrated to the design method for a certain input. Right. Having said that, I'd like to show a few research works that have been carried out, and it is from these research works that the calibration of the various factors are developed. The first one I'd like to talk about is the Montana State University. This is a full-scale trial on site where that's the truck and the wheel plan view that are being used. And this is a multiple product where different manufacturers have contributed materials, and then the university will do the research on a fair and open basis. Examples of a subgrade, in this case, you have got fines that are more than 50%, and that's the base cost material that meets the specifications of a few highway authorities in the States. This is an interesting chart. The task report actually mentions different products and names, but for the purpose of not showing them, I have just grouped them. The control is where no geosynthetic is used, and a combination of geogrids and geotextiles are used. And here I've grouped all the geogrids into a shaded area, and this is the Mirafai RS580i. The lower this curve is, the better is the performance, because then it chalks up the same rut depth over longer periods of time. And the bar chart on the right shows that Mirafai RS580i has got a traffic benefit ratio of 10.8. That means the road can last 10.8 times longer when you compare with and without the use of the Mirafai RS580i. What I'd like to point out is that in this test, the Mirafai RS580i outperformed all products, including the best of geogrids in the market. Another example of a test program is at the Kansas State University. This is for a paved road section, comparing different combinations of thicknesses of different materials. And here you can see that for controlling deformation of 12.5 mm, there's a traffic benefit ratio of 2.3, and likewise, you can work out what is the base cost reduction if you want to approach it from that angle. Now I'd like to talk a little bit about roads on expensive clays. The loss of pavement shape due to moisture changes in expensive soils can lead to significant pavement distress and often the need for rehabilitation. And there are a few ASTM standards that defines what is swelling and non-swelling clays. But a simple guide is this Australian guide, PIN 57. It relates expensive soil, how severe it is to liquid limits and plasticity index and so forth. So this is a very useful table to refer to. And what are the problems? Differential moisture content in expensive soil subgrades can cause waviness and cracking in pavements, especially in the pavement edges. What is happening now is when you have got rain, the soil at the edges gets wetted up much more and expands up much more. So you have heaving and you can crack the pavement, as shown in edge cracking here. And also, something can happen in the middle of the pavement. If there are uneven moisture distribution in the expensive soil, then you can have, it can cause heaving along the pavement, both of which are undesirable. And what are the solutions for that? Before I get into that, I'd like to talk about the difference between gravitational and suctional in-plane drainage flow. In gravitational drainage, you need a water height difference to drive the water to flow. But for that to happen, it means that the soil is already saturated and weakened. Whereas in suctional drainage, you do not need the soil to be saturated. Suctional drainage is caused by capillary action, and it draws water from the soil and then takes it out and release to the atmosphere due to difference in potential, suctional potential. And the fabric that are able to do this, an example, here you have got the wicking to textile, the H2RI, and you have moisture that can flow horizontally along the fabric, as well as it can flow upwards against gravity. How is it used in the site? Here's an example, reference on book. It's the State Highway 21 in Texas, where edge cracking is very common. They have to come and repair it over and over again because it's built on expensive clays. And in a test section, different fabrics, geotextiles were used. 140 NC is a non-woven. HP 570 and RS 580I are high modulus reinforcing fabrics, and H2RI is a high modulus reinforcing fabric plus the ability to control moisture. And you can see here what has happened is that with the H2RI, the moisture content spread is so narrow, as well as the mean or average moisture content as well. So this is what, and it's been shown to be effective in preventing this edge cracking of pavements over the expensive soils. And lastly, I would like to talk about very quickly the railway research at Chengdu. Here, this is a simulated plate loading test for high-speed rail, which where we compared three different situations or models. The control has no geotextile, and there's a standard of 150 mm of sub-ballast and 300 mm of ballast on top. And then model 2, there's an inclusion of Mirafy HPC 2000, which is a composite of a non-woven and a high modulus woven stabilization geotextile. And model 3 has got the inclusion Mirafy HPC 5000, which is a composite of non-woven and a high modulus subgrade stabilization plus moisture control geotextile. And I'd like to show you the performance. The black line shows the permanent settlement with load cycles for the control, and the red line shows the performance of Mirafy HPC 2000, and the green line shows Mirafy HPC 5000. So you can see here there's a 9 times improvement using HPC 2000 and a 13 times improvement using Mirafy HPC 5000. And also what was measured was the degree of fouling in the ballast material. And here you can see the blue column is a control, the red column is HPC 2000, and the green is HPC 5000. And while it is the non-woven that is responsible for the anti-fouling control, we also see that when you have got wicking capability, it reduces the subgrade moisture content, and it also helps to reduce the amount of dynamic pumping upwards. And we have come to the end of the presentation. Thank you.
Thanks, Link, and thank you, ladies and gentlemen, for staying on with us. Before we head over to the Q&A session, please allow us a couple of minutes to compile the questions that are still coming in. In the meantime, we would appreciate your response in this polling session for our further improvement. This is where you can also indicate your interest in the video recording and the certificate of participation. The polls will close in about 1.5 minutes, and we'll be back right after this. Thank you all for participating in our polls. We will now enter the Q&A session. So we have many questions coming from the audience. So first question, Tarling. What type of piles are typically used for pile embankments, and what is the typical pile spacing?
Thank you for the question. There are many types of piles that are used for pile embankments. Typically, concrete piles are commonly used, and they can be in the form of driven piles, even jacked-in piles, and sometimes cast in situ piles. But having said that, there are other forms of vertical support systems that are used, including the cement clay mixed in situ columns, and also timber piles, treated timber piles in some low load conditions. On the question of pile spacing, I guess from construction experience, typically you would find that they can be anything from 1 meter to 2.5 meters, or even slightly more sometimes. It really depends on the problem or the project that you're facing, case to case.
Okay, next question. Is the woven geotextile, biaxial or uniaxial geogrid for different types of pile caps?
That is a very good question. Firstly, I'd like to again go back to the point that you need to know whether you are requiring that reinforcement in one or two directions. If you are having a linked pile cap or capping beam, then typically you only need the reinforcement in that one direction. When you're having individual pile caps, then you need to have reinforcement provided or reinforcement strength provided in two directions. Now, woven geotextiles up to the strength of 200 kilonewton per meter can actually be manufactured with equal strength in both directions. However, having said that, because the need to join, when you seam, typically you can lose half that tensile strength. So what is common in practice is that you would ignore what is the strength in the cross direction. And also when you go into higher working loads required, for example, if you require tensile strengths of 600, even 800 in one direction, and say 400 in the other direction, it is not possible to manufacture a biaxial product that would fit that. So the general practice is that we would only use the machine direction, which can be any strength up to 2000 kilonewton, and the cross direction would only typically have either 50 or 100 kilonewton per meter. The fibers are provided there, and they give that strength, but it is merely to provide structural stability to the fabric, not to take up tensile strength. So when you have a case where you need the reinforcement strength in two directions, you lay reinforcement in both directions using different rolls to meet those tensile strength requirements.
Okay, next question. Why can't PET do the job of HPA even though it meets the tensile modulus of HPA?
That's a very interesting question. As you can see in the presentation when we were dealing with subgrade stabilization. In subgrade stabilization, you have such a variable requirement for geosynthetic performance that includes separation, that includes dynamic filtration in the case of anti-fouling, and also reinforcement and lateral spreading and so forth. So products that are designed for subgrade stabilization can be quite application specific. So coming back to your question, PET generally is designed to give very high tensile loads for basal reinforcement of embankments and pile embankments, and they typically go at least 200 kilonewton per meter. In subgrade stabilization, you do not need that high, and typically you are talking about products that are 50 to 100, but they require other things that PET may not provide. For example, PET have a generally smoother surface that does not provide the lateral restraint, and with HPA, it is very robust. You can take the compaction of aggregate above it without much damage. So it is not possible to compare the two. And when you are using, when you need a geosynthetic for subgrade stabilization, then I would recommend the HP series or the RS series.
All right, we have another question on pile embankments. For embankments, does the arching of soil occur with any type of fill soil, or does it happen with granular soil or frictional soil such as sand?
Another very good question. Actually, arching happens in both cohesive and granular soils. However, in a zone that is directly above the reinforcement, sometimes design engineers prefer to go for granular fill. And the reason for that is that if you use cohesive fill, if it is wetted up, then you lose cohesion. And then when the cohesion is low, the arching will also be low for cohesive soils. It does not mean that you cannot use the general fill directly above the reinforcement, or you have to only use granular fill. It depends from case to case. If you are in a very arid area where the risk of soaking up of the backfill material is very remote or none, then it's perfectly okay.
All right, next question. What is the general guideline for geosynthetic overlaps in subgrade stabilization application?
Right. The general guideline is that if the subgrade quality is not too bad, by that we mean if the CBR is greater than 3, then a nominal overlap of say 300 mm or 1 foot would be sufficient. And as it goes weaker, then that needs to be widened. For example, at a CBR of 1, we would recommend an overlap of 600 mm or 2 feet. And below that, it may be more economical to sow or in some cases like the super soft soils, sowing is mandatory because even if you have very large overlaps, it will still open up because the ground is moving and heaving so much.
Okay, we have one final question. What are the differences in the design approach of a road constructed directly on soft ground as compared with a road constructed on embankment that passes through soft ground?
The main differences are here. When the road is built directly on soft ground, the traffic imposed load has a more direct impact on the soft ground, and especially in respect to the resulting stability or the deformation of the road surface. The inflow zone on the ground is also relatively shallow. We are talking about maybe 2 feet, 0.6 meters to maximum a meter or so, because the width of the the imposed load track is small. When the road is built on embankment, we can choose to have good fill, and subgrade stabilization is less of an issue, but the weight of an embankment then ultimately may cause stability and settlement issues on the soft ground below. Here, because the embankment width is very wide, so the influence zone can go to much deeper depths, and sometimes you have got slip failures going 5 meters or even more, and the settlement effect of compression can go even deeper, and up to 20, 30 meters. So that's the basic difference of the two types of so-called engineering application.
All right, thanks, Darling. Thank you all for your questions. For questions that we were not able to respond given the time constraint, well, don't worry, we will get in touch with you after the webinar. So just a quick reminder to those who have already registered for our webinar next week, remember to tune in to Water Infrastructure Protection Part 1 and 2. There are also a series of webinars that are still open for registration, including that of reinforced walls and slopes, and GCLs for ponds and landfills. You can register for these through our website if you are interested. So ladies and gentlemen, we have now come to the end of our webinar session. Thank you for your participation. We hope you have found the presentation useful and informative. Please feel free to connect with us. Contact us if you have any inquiries, and let us know if there are any other webinar topics that you'd like to know more about. So hope to see you all again next time, and we wish you a safe and splendid day ahead. Thank you.